high.
All right. Can you guys hear me? All right.
I never put them there. Thank you.
Good morning, everyone. I'm Pierre Lermant with Akamai. I'm an enterprise architect. And today we're going to be talking about the modeling of web content. Basically, how long it takes to download website resources. So why is it important to compute this value? Well, it's important for IT organizations for at least two reasons. One is you need to understand IT managers when they have to make decisions whether or not to open a new data center. They need to get as much data point as they can to figure out what the impact. Say they have a lot of users from Europe. What is the cost of, say, opening or not opening a data center in Europe as opposed to in the US. Another reason is that from the origin infrastructure, there are a few parameters that are important to set correctly to improve the web performance of your sites. And I think everyone knows here the importance of the performance. So the third reason I would say why I spend time on this model is that I couldn't find one on the internet. These days you can find just about everything. It's pretty amazing. You look for anything, you'll find it. You just type a search. But I was looking for something fairly simple, usable, yet meaningful as far as finding out how long it would take to download a specific piece of content from an origin to a client. And I couldn't find anything satisfactory. Either the models, as it's listed here, well, they are too simple. We know it's going to be bound by the speed of light. And then if you dive into the TCP mathematics, it can be a little overwhelming. It's pretty well understood, actually. But for us, we want to think that we actionable rather fast. It wouldn't cut it. So as a result, I couldn't find any practical ways of anticipate how long a web resource would take to download from an origin to a client. So to kind of prove my point, in a way, I'm going to ask you, and you just keep that to yourself, how long would it take to download a 50K resource, which is kind of on the large size, but somewhat typical resource that are pulled from the websites, across the coast. So say the origin is in New York, and you have the client here. How long would it take to get this 50K resource? So keep that in mind, and we'll see how well people fare. And the answer, of course, is also it depends. And why does it depend? Is because there are a lot of parameters that come into play when trying to predict how long a resource is going to take to flow from the origin infrastructure all the way to the client. So here I name, it's fairly comprehensive. It might not be the whole thing. I disregard the DNS lookup, for instance. But from left to right, where you have the client settings going to the last mile bandwidth and latency, RTT, which is a round trip time, and latency, I'd be using the two in the same meaning. Then you have the middle mile that can stretch for thousands of miles. And finally, the origin infrastructure, which typically is pretty well connected to the backbone, but there could be also latency to fetch the content. And there's also parameters around the connections, either persistent, and also what is called the initialization windows, window for a TCP. And we will talk more about this. And at the top right, obviously, these are kind of global parameters. The distance between the server and the client is going to matter. Whether you're secure through HTTPS or not secure is going to impact your download times. But of all those parameters, some of them, not surprisingly, matter more than others. And we'll start with the one that actually don't really matter. You'll find corner cases where they do matter. But a model addresses the 80-20 case where we want the model to work for 80% of the cases. And that says that the last mile bandwidth, right, that is pretty strongly advertised by the AT&T of the world when you buy, a subscription, actually we're at a point where it does no longer matter for the bulk of us. So on the left-hand side, it says that, the page load time as a function of the bandwidth, the minute you hit, 4 or 5 megabit per second, the gain you have loading web pages. We're not talking videos, right? We're specifically focusing on websites. It becomes marginal. And then on the right-hand side, I pulled this from the Akamai State of the Internet, the latest data from Q2 2014. And you see that worldwide, the average is 4 megabits per second. So I think we're lucky enough that we can see ourselves as better connected than the average, especially at our home. Again, the last mile bandwidth that you hear quite a bit about, again, when it comes time to buy in subscription, does not really matter. And another parameter you might hear about, it's called the buffer receiving window. So it's basically the amount of data that can be in flight between the origin and the client. When the client buffer is full, it's going to say, no, don't, slow down, I cannot keep up. And it's typically set to 65K. And as we know, most web resources, individual resources, are smaller than this. So it's not a major factor. Network loss. Network loss here, I kind of had to assume it's negligible. Again, due mostly by the small size of the entities, right? We'll see that it only take a few round trips, and during that time, usually the connection goes up and doesn't reach its peak throughput. But in real life, you do have losses once in a while. Actually, when you have losses, sometimes they manifest pretty brutally, and the degradation is intense. To support my case that most web resources are fairly small, I pulled that from httparchive.org. If you don't know, this website is very useful for global metrics about websites in general. They pull data from the top, I think, 10,000 websites. And you see, Flash aside, and Flash, slowly but surely probably is going to die down. You see that the resources are small. And the ones that are not cached, typically the HTML, you see that on average it's pretty small. So now moving on to the parameters that do have the most impact. Well, the fact that the connection is new or reused, and we'll see actual numbers, is really critical as far as determining the time it takes to download the resource. If it's secure versus non-secure, and I'm sure you guys know this, and we'll see some graphs about this. And if we talk about the round trip times, again, we're going to ignore the first mile, which is the origin, because we don't control. Obviously, if it takes 10 seconds to pull the data, you'll have to add 10 seconds to this model. Last mile latency can be down to pretty close to 0 at work. If you're connected to the backbone, you take a measurement. We're talking anywhere from 0 to a couple of milliseconds, all the way to hundreds of milliseconds if you go through cell phones, older technologies. What we'll be focusing on also is the middle mile RTT, which, as you will see, has a tremendous impact over the long distances. So the middle mile is between your ISP provider and the origin, right? And we'll see that over long distances, this parameter actually might have the biggest impact on the model. The last two that have the most impact, and we'll be talking about more, is, as I mentioned, the so-called TCP congestion window. It's basically a parameter at the origin that dictates how fast you're going to ramp up the traffic between the client and the origin. And all the builds had parameters set to low values, which means that before you can have a significant throughput, you had to go through a lot of round trip between the client, acknowledging a few packets and sending a little more. So it's something we're going to have to keep an eye on and make sure the origin is set correctly. And just to be complete, setting the obvious, the size of the resource and the distance the resource has to travel. So the middle mile RTT is probably the main reason, the biggest reason why I couldn't find, quote unquote, a good model on the internet about this problem. It's because you cannot approximate it by a mathematical equation, no matter how complex. And it's mostly the reason why it's hard to model. It's because the way a request is going to travel through the public internet, right? And it's driven by the BGP protocol. It's not necessarily driven by performance in mind, but it's driven by business rules. Basically, between ISP, they trade traffic, or they say if you go this route, it's going to cost you less than going that route. So eventually, the request gets it to the destination here. I'm going from the US to Germany. However, it's very hard to predict, and this is going to be, I would say, that the main contribution of this talk is that we spend some time building a model to try to determine this round trip time of the middle mile. And here is the setup. So the red dots are pinging agents, right? So throughout the US and throughout Europe, we mostly focus the pinging agent in the US and in Europe for now, because it is a bit more reproducible. So these ping agents, we leveraged the huge footprint of the Akamai platform to ping a bunch of our servers around the world. And the number of servers were roughly matching the population density, so we had meaningful results. So obviously you'd have, and I tried in my graph to represent this, you'd have, for instance, a lot more server in the US as targets, say, as in Australia. So we did all these pings that we repeated over time. And here is a very simplified distribution, but to give you, an image speaks always better than words. The typical distribution of the relationship between the round trip time over the distance, right? The goal was try to say, well, is there a simple correlation between the round trip time and the distance, given all these parameters and these ISP business relationships? Is there, at a high level, something simple we can grasp? So this is, again, we went from almost zero. I mean, we started at 500 miles, because if you go very close to if the client and the origin are very close, then the path could be really wild. But the good news is that if the server and the clients are close, you don't have a performance problem, because the latency is going to be short. And the main result here is that for distances not too close, I say 500 miles just to set a boundary here, is that we could derive that the RTT, right, the latency is about 3.1% of the distance in miles. So if you remember only one thing of this talk, is that when people ask you, what's the latency between point A and point B, ask the person how far apart are they, you multiply by 3, and you won't be too far off. As an example, again, to support the theory here, between here, San Francisco, and New York, you have about 2,500 miles. At the speed of light, it would be 27 milliseconds, and the actual round trip time is about 3.1 times 2,500. You round it up, we're talking about 10%, 15% accuracy. But 80 milliseconds, and I'm sure people in the DevOps here, they probably acknowledge that talking about round trip time only, not the whole big result, but round trip time is around 80 milliseconds. A couple more points about this diagram. What was interesting is that we repeated the experiment over time, like a few months apart, and this number stuck, which was good. So we look at the global level, we don't have that much variation, at least short-term variation about this RTT. And another interesting point also is that it did not vary much across geographies, right? The 3.1 was applicable to Europe, North America, and South America. Again, I don't doubt that in some regions of the world it would be probably significantly different, but we do a lot of our businesses in those regions. So going back to the parameters that I said matter the most, this is the typical diagram, and you've probably seen this. What happens, but for the people that are fairly new to the TCP concepts, this is how it works. When the client initiates a connection, there is synchronization happening if it's HTTP. So there's already one round trip where basically the client and the server says, okay, we understand that we're going to exchange information. If it's a secure network over HTTPS, you have two more round trips here in purple, where they're going to say hello, and they're going to exchange information about the cipher, basically how they're going to encode the information. And it's not till the bottom here when you actually trigger the GET, right, or the POST, where you actually send the data, your HTTP request to the origin. So you see that, and I try to color code to make it fairly simple. It takes 2 round trips just to get any information back from the origin for a new connection in HTTP, and 4 round trips for a secure connection. This is the follow-up, and this is follow-up. And this I haven't seen either. I saw the first one in the web. I mean, I redrew it to make it more colorful. But here is really to bring the point home about the congestion window at the origin, right? So again, it's kind of try to size it according to the amount of data. On the left-hand side, you see that the congestion window is set to 3, meaning, from the initial post, we'll send back 3 packets. They're going to be acknowledged, and then we'll send 6. It's always a double until basically the thing breaks down and packets get lost. But that was one of the assumption that since after just a few round trips you get the data, we're going to assuming there is no loss, so there is no restart. However, if you have the congestion window set to 10, you see the huge difference pretty quickly. You get 10, 20, 40 packet, and a packet is typically 1,500 bytes. I think the actual payload is 1460, but just remember 1,500 bytes. So if you have contents that's not minuscule, in the tens of K, you see the impact as far as number of round trips that the congestion window can have. And here it encapsulates all this data in a graphical form. That also I've never seen that on the internet. Hopefully, it can be useful for some people to get this. And here, what it lists is the amount of data you can download per round trip, right? In the different use cases we just surveyed. So in blue, it would be a small congestion window through HTTP, and so on and so forth. And we can readily see that and all the colored lines are for new connections. The black line, right, it's existing connection, and we saw that in theory it's only bounded by the client receiving window, which is 65K. So in one swoop, if your connection is open, you can transfer 65K. But the worst case, see if you have an old server that you haven't upgraded in a long time, and you go through HTTPS, to download our 50K resource, it's probably going to take 6, 7 round trips. And you saw that a round trip, across coast is 80 milliseconds. So it does add up. So I thought it was an interesting graph to really capture the impact of the congestion window, the fact that it's HTTP versus HTTPS, and mostly if the connection is open or not. And the CDNs, they obviously take advantage of this. CDNs are thought of, again, if you're not super familiar with them, mostly for caching static content. And they do obviously an excellent job. GSS images, they're cached 99 point something percent. What is not always known is that by leveraging a pair of edge server and what I call CDN intermediary, you can, and keeping these connections open between something close to the client and something close to the origin, you can make sure that you keep these connections open for very long, and you maximize the odds of having the request leverage this open connection. So this is how it typically, so it's not to scale. Typically the client and the edge server, they are within, say 20 milliseconds. About the same between the CDN intermediary and the origin. It depends on the footprint of the CDN network, but we're talking in anywhere from 10 to 20 milliseconds. And obviously the space between the two can be as big as we want. Like in our case, to follow on with the example of 2,500 miles, they'd be 2,500 miles apart. So even if the client and the CDN connect with a new connection, the CDN will have all those connections between their peers open, and they're kept open for a very long time, and then you don't incur this so-called slow start of the TCP. So the message is here, for customers that are far away, a CDN can speed up the delivery of your content, even for non-cacheable content. So going back to our 50K, here is, if you plug in the numbers, you see that over, and you have to read the bottom line because the question, we had to qualify it. So 2,500 miles, new connection, HTTP, no network loss, and no ignoring the first and last mile latency. You see that it would take close to 400 milliseconds. I mean, it's an eternity when everyone says, oh, if my page doesn't load in 1-2 seconds, I'm losing users. Just this one resource would take 400 milliseconds. If you make sure that you set your congestion window at the origin to 10, and I would say most servers now, definitely all the more recent build, they set to 10, you always shave off 300 milliseconds. However, if you go through a CDN and the CDN happens to have this connection open, which is not a guarantee but very likely, you can see the tremendous differences just by virtue of reusing the connection during the middle mile, which can stretch many miles. All right, so to go over what we just saw, again, median middle mile RTT, I said it was 3.1%, but for all practical purposes, 3% is probably easier to remember. Again, if people ask you, if it's 1,000 miles apart, well, 30 milliseconds, you'll be in the ballpark. Try to remember this, and again, it's somewhat backed by the data we found on the Akamai platform. The client bandwidth and TCP buffer size are not really a bottleneck. The congestion window is critical at the origin. At Linux, as of 2.6.39, it was raised to 10, which is already a while back. But again, some infrastructures don't change much. Do verify that you have this set to 10. And again, the dramatic difference between reused connection or brand new connection. And the message is that please see if you can keep your TCP connections open. Sometimes it's not possible. Sometimes you think it's not possible because of security or because of resource issues. But really think twice because the benefits to your overall performance is really dramatic. And if it's not possible and you have a lot of end users far away, do consider leveraging a CDN. So now we're going to do a little bit of a live model. So what I did here is put this model into practice, and the practice is going to be a graph. So what I'm showing here, it's a public link. It's at www.akamai.com. So you're welcome to go there, and the model is really simple. All the business logic, if you'd like to draw the graph, is in a JavaScript, so you can pull the JavaScript and modify it as well. But basically, the top parameters we talk about are listed here. You see, I stick with my 50K resource, and a non-secure connection. I mean, you can read the parameters, and what it does here for you is that it's going to draw two graphs. The first one is for the size that you selected. It is going to take you according to the model, right? The time difference you'd see between the public internet, aka the BGP route, and if you hit an existing connection within a CDN. And you see again, for long distances, the difference can be pretty dramatic. What I did also to kind of capture the nonlinear effect of this slow start where we saw, it sends a 3 packet, then 6 packet. It's not linear. You have this kind of step effect. And this bottom graph here shows you for a fixed distance this time, 25 miles again across coast, depending on the resource size, how long we can anticipate it's going to take to download the resource between the client and the origin. And you see again this step. So if we go to the 50K resource here, we see about 200 milliseconds here as opposed to 500. And well, the purpose of this is obviously to modify these parameters. So you see, just as an example, you see that we had the TCP frame number 3. We saw like it took almost 1 second at 5,000 miles. And if you boost it to 10, as we saw, you can shave off significant time just making sure the congestion window is bigger. And same thing with secure versus non-secure, and so on and so forth. So it gives you a model if you want to have somewhat harder data. Again, when you try to make decisions whether or not you should open a new data center, or what is the cost in terms of performance for your end users, and so on and so forth. So again, feel free to go consult. And even, again, grab the code as you wish. All right, so the presentation is finished. I do have time for a few questions. Anyone? Anyway, I'm going to be hanging around here if you have more questions. Well, thank you for attending.